All right. Yeah, thanks everyone for coming. Very happy to see some familiar faces and a lot of new ones. I'm Sergio Casas, and I'll be presenting the session on motion forecasting, which I'll refer often in the industry we do as prediction indistinctively. So prediction is right in the middle of a traditional self-driving pipeline, and it basically takes the inputs from perception, as Ewan just presented us, typically in the form of the object detections and tracks, so essentially describing the past trajectory of an object. And it provides estimation about the future evolution of the scene, so that planning can then assess the risk of potential maneuvers based on those probabilistic predictions. And here you basically have an example of how this typically looks like. What we are showing here is the ground truth future trajectory of different agents in the scene. And why this task is interesting, we'll talk a bit more about the challenges later. But for example, here, even in just one snapshot, you have a vehicle performing a U-turn, and a bit ahead, you have two vehicles nudging, basically lane changing for a vehicle that is yielding to traffic before it can perform the unprotected left turn. So there's a lot of complexities, a lot of interactions between the different agents in the scene, as well as the map, and everything needs to happen from sensor data, essentially. So the agenda for today is we'll talk a bit more about the prediction task. We'll focus on the challenges, a classical approach, and then machine learning-based approaches, which dominate today. We'll dive deep into how can we represent at the scene and basically learn a rich representation that allows us to then predict very expressive futures. And finally, we'll look at how we model the future and how can we essentially capture the multiple futures. How do we model uncertainty? We'll talk about the fact that the ego itself can also influence the behavior from the others. In the scene, we'll talk about joint prediction. And finally, alternative representations like occupancy to the trajectory, the typical trajectory representation. So yeah, let's go right in. Yeah, so the main challenges are partial observation. So basically, as you can see, there's a vehicle in the foreground here that is occluding the vehicle behind. And so for the vehicle behind, we only see a tiny portion of it. So most likely we will have either like a partial history of its trajectory, or it won't be well localized. So essentially the inputs to prediction will be noisy. And if this vehicle, for example, the occluded one, were to left turn, that it will become relevant for the ego plan. Sorry, and I refer to ego and self-driving vehicle indistinctively for the robot that we are controlling. The second one is unknown intentions. So we don't really know where other agents are going. They have a route, of course, they probably are following like some GPS instructions or whatever, but we don't really get access to that. So in that scenario, for example, just from the past motion, it's very hard to infer whether the vehicle will turn left at the intersection or will continue straight. Of course, there are cues, like for example, if they are braking before getting to that dash line, it probably means they are going to turn, and we can use those. But at the end of the day, we only have partial information. And finally, interactions between different agents, or negotiations. In this intersection, let's say we know, which we don't know in practice, but let's say we know their goals, and it's these stars, and they basically are crossing paths, right? And we essentially in prediction, we need to understand how they are going to negotiate, if there's anyone that is a bit more aggressive and therefore might have a higher chance of going first, or the other way around. So the classical approach to prediction, I guess before neural nets took over, it's just to unroll the tracker state. So you have some tracker that has some probabilistic modeling, potentially like a Kalman filter, and we can then, based on that kinematic state that we've tracked, we can extend this trajectory forward. So here in the plot on the right, you see the gray trajectories are the past trajectories, and then the red trajectories are predicted by a very simple model, which is just constant velocity. And you can see, actually, in most cases, it does pretty well. But then on the more diverse ones, it cannot really capture them well. And maybe some other more complex ones for vehicles, for example, you can assume constant turn rate acceleration instead of constant velocity. So the strength of this is that, I mean, first, it's very simple and super fast, which is also important for a real-time system. And it can incorporate some prior knowledge that we have about typical behavior, like typically people continue straight. However, you cannot capture the diversity of the real world. And the worst part of this is that actually the cases that we care the most about, safety critical ones, are typically those that don't follow standard behavior. So this doesn't really work great for those. Then machine learning based prediction essentially just takes the past trajectories as tracks and a high definition map. And we'll talk about how these get encoded, but essentially we have a neural network that predicts the future based on this. So essentially the neural network here is replacing prior knowledge with data. And we are now modeling that data and are very reliant, of course, on our data sets. So the limitations of this is that the detections and tracks are still noisy. These are coming from another system and they are not perfect. So we need to model that noise, or as we can see, there are some alternatives to bypass this. There's information loss in those tracks and detections. They are very low dimensional and they don't capture like details in the sensor data, appearance, even turn signals potentially and things like that. So a lot of that, this prediction standard traditional pipeline prediction doesn't get to see all those details, which makes the problem even harder. There's redundant computation because there's typically a detector, a tracker, and a prediction model, and they are all separate networks that run cascading. And they actually share, they need to do a lot of the similar reasoning. Like, for example, for tracking, you need to understand time. And for prediction, you also need to do the same. However, that computation is redone basically in the original traditional pipeline. And finally, this system is very complicated, hard to debug, maintain from a software engineering perspective too. So the alternative is to join perception and prediction, which our lab pioneered since 2017, I guess with this 2018 CVPR paper at the bottom. And the key here is to just bypass or unify basically perception and prediction into one neural network that go from temporal sensor data. We'll talk a bit more about how this is actually represented in more detail, and the map. And it predicts both the detections as well as the future predictions, not just the future predictions based on the detection. So this is still interpretable. We are still outputting the same outputs, but now it's not as cascading. The uncertainty can propagate downstream because basically through the features, since this is essentially now a multitask problem. And the computation is also shared because this joint perception and prediction neural network has a backbone that does most of the computation and is shared for both tasks. Next, we will go into a lot of detail of how do we encode the scene to basically be able to predict with our neural net. And the first part we'll cover is how do we encode the past context. So this past context can be in the form of trajectories in the original traditional pipeline or in the form of sensor data in joint perception and prediction. So when considering the traditional pipeline, we essentially come down to this. We have sensor data, detection and tracking. We get the past trajectory of the actors. We perform past trajectory encoding, which is highlighted in blue, and it's what we are going to be talking about in the next few slides. And then we'll do some decoding, which comes later. We will talk about more in detail later in the presentation. As Yuan mentioned, also for perception, one option is to represent these tracks as rasters. And so these are multi-channel bird's eye view, typically images local to each actor that represent its past trajectory, but also the past trajectory of the agents around it. And you can encode it very simply with a two-dimensional CNN. This is super simple to implement, but it's also very memory intensive because if you have a big receptive field and you want also high resolution to not miss the details, this ends up being expensive. And finally, we are still in this paradigm where the detections and track are noisy, and so these errors will also accumulate during the prediction phase. Alternatively, we can encode the tracks as directly trajectories or vectors. So you can think of this as a sequence of waypoints or a sequence of vectors, and you can use recurrent neural networks or one-dimensional CNNs or graph neural networks transformers as well if you use positional encodings to encode the ordering. This is a very compact representation, but it's kind of hard sometimes to encode everything you want from a past trajectory. Like let's say your tracker has some uncertainty, and unless it's Gaussian, which you can then, it's parametric, so you can include. But if it's something a bit more complex, you could rasterize it, but it's hard to express in a few parameters. And it continues to have the same issue, of course, of the noise in the input. So the alternative is to go directly from sensor data. And basically we call here a sweep. What we call a sweep is a 360-degree scan of the scene. And the challenge is that the sensor is moving with the vehicle, right? With the ego as it moves. And so if you directly stack, let's say, the point clouds in sensor frame, it doesn't make a lot of sense with respect to the dynamic actors around you. But if you perform motion compensation and basically essentially plot all the point clouds from the different sweeps in the same consistent coordinate frame, like we did in that image, then the motion of the objects is very obvious, even from the sensor data, right? Like the only thing we are doing here is plotting in different colors the different time steps for the past point clouds. And you can clearly see that this vehicle is going sort of a constant velocity, and you can definitely infer the speed if you knew the resolution of the image. So there's very rich information, not just about motion, but also about appearance, occlusion, uncertainty, everything. So the way we encode this is by basically we take this multi-sweep LiDAR in this consistent coordinate frame, we voxelize it, and then you get basically one 3D voxel per time step, right? You can stack these, so you still get a 3D tensor, but it has the Z dimension and the time dimension stacked in one. You can perform some convolution in that, get scene features. From these scene features, you can perform object detection, which gives you those candidates bounding boxes. We can consider a region around them and use, for example, something like rotated ROI line or any other pooling mechanism to get these feature maps per actor, per agent. And finally, with some convolutional neural net plus pooling potentially, you can bring this feature map into a feature vector. And from now on, we'll refer to this feature vector as agent features. And this is just a nice abstraction because now, whether we come from sensor data or from past trajectories, we can extract these agent features, right? So the rest of the talk basically doesn't assume one or the other. And you just basically, we have this abstraction that we have some descriptors of each agent. The simplest form of prediction is to go from basically these agent features, which are like these one-dimensional feature vectors, pass it through an MLP that is shared across all agents, and just predicting one trajectory for each of them. And you can think of this trajectory just as a vector of length 2 times t, where 2 comes from the XY coordinates in bird's eye view, and t 40 time steps into the future. And so, I think this is the missing slide, right? Okay, we'll see there's a similar video in a few slides anyway. So we'll talk next about how do we encode the high definition map. So we saw basically the branch at the top, right, a couple of slides ago, and we can also encode the map and fuse it into this pipeline. And so that's what we are going to talk about next. As presented also in the perception session, similarly, we can raster the high definition map. And as you can see, this can include in the images on the right, this can include very rich information about the semantics of the map as well as the geometry. We are plotting, for example, there like the lane direction, like the orientation. You can also see at the bottom right, there are some traffic light states. That's why it's green or red. So these are very flexible. You can raster basically any geometry and semantics. It's simple to implement. It's very natural for dense prediction. We'll talk about in the later part of the presentation, like occupancy. But the 2-dimensional CNN that you typically use to extract features from this has a limited receptive field. And of course, we are in an onboard application, right, that needs to run fast. So you don't want to also stack like just as many layers as you can. So what ends up happening is that you typically trade off by reducing the resolution, which introduces quantization errors, and this can be quite memory intensive. So a very simple approach using this is that you take your raster map, you pass it through a 2D CNN, you get map features, and then if your raster map was rasterized with the same resolution and dimensions as the voxelized LiDAR, then you can just trivially concatenate them, like fuse them by basically either concatenating them channel-wise or by summing them, and then passing it through another CNN, the green one in this case, to fuse them. And from these fused features, we just do the same that we discussed before, basically have some MLP predict. And one thing that we've lost from the traditional pipeline is that now we are tied to these limited history of the point clouds, because point clouds are very high dimensional. So you can also just not take as input like the 100, let's say 10 seconds, right, worth of history directly into the two-dimensional CNN, because it would be too expensive. So in this work, it was proposed how to basically introduce tracking in the loop back into this joint perception and prediction framework. So far up to here, it's the same that we've presented. We have our shared, fused features from LiDAR and maps, and we can perform object detection. Then we can have a memory bank, essentially containing our tracks as well. And these tracks can contain also learned features, not just the past trajectories of the agents. We can then perform matching between the current detections that we just detected from this like new input, right, with the tracks in the memory using some learned cost function. And we can also refine the trajectories in the memory bank based on the new observations. And once we do this, now we can actually have a much longer history through the memory bank. This architecture essentially brings the benefit of the traditional pipeline into this joint perception and prediction framework. And here are some results. So essentially, I believe these are predicting 3 seconds into the future, and we are using the map, as you can see. And now, unfortunately, we couldn't play the video earlier, but these are a lot more consistent over time thanks to the tracking. And they also follow the map a lot better since now we are fusing that information. An alternative to the raster representation is just to represent the high definition map as a lane graph. And here you can think of lane segments as nodes. So we take the high definition map, which contains some center lines and boundaries and topological relationships, and we can sample essentially like at some even separation, we can sample points in those center lines and connect them, let's say, by considering their neighbors, like successor, predecessor, and then left and right neighbor. And this gives us a row graph or a lane graph. And we can encode this there are many architectures proposed for this, a few of them cited at the bottom, but with a graph neural network or transformer, one can encode this. And these have been shown to be super parameter efficient and require very lightweight preprocessing, namely just this sampling that I was talking about of the points. It does need a bit of handcrafting of the features to make sure that in this new compact representation, we still preserve most of the semantics that I was showing before in the rasters. It is a bit hard to fuse with sensor observations, or at least it was before attention came up. And I believe now cross-modal attention makes this a lot easier, although there hasn't been a lot of exploration. Representing certain relationships can be a bit hard as a weakness, because, for example, if you have like some curve and like, let's say 2 lanes are not connected, they look the same if they are not connected, but they are very far away. That is, they are pretty close in distance. They just won't be connected by an edge in the graph, so it will be hard to propagate information between them, which with a raster it's a bit more flexible. But this is super efficient, and this is actually the state of the art for most works. Now let's dive a bit deeper into like the actor-to-actor interactions. We saw that case at the beginning, for example, with the vehicle nudging. And here's another example, but we could really go on and on. So the vehicles are approaching the intersection at a pretty much constant velocity. So if you predict them independently, the best guess is that they will continue their speed and collide right into each other, right? But in practice, our prior knowledge, we know that's not likely to happen. One of the two will likely break. So what we can do is that we encode the past, and then we perform some form of message passing between them. And we then predict based on these updated features from the actors from the agents considering each other. And hopefully through that, we can get information about which one is likely to break, perhaps based on like small speed reduction from one of them, and so on. And so how this fits into the overall framework, we saw before how can we abstract past context and map encoding into these agent features. And now from these agent features, we can do this interaction reasoning and finally output some predictions. So the early days of interactions was social pooling is kind of the pioneering work. And basically what we are doing here is that the features from neighboring actors are scattered into this social tensor that you see at the bottom. So at the bottom, we are basically considering updating the features or the representation of the black agent. And we are considering the blue and the orange one as their neighbors. And here it was an initial mechanism to model this interaction, which basically just took the features from these two, blue and orange, and make them into this tensor. And finally here do some pooling to understand the interactions. And although this, of course, has been improved over time, actually in spirit, this mechanism hasn't changed that much. You are essentially aggregating information across your neighbors. It's just that the modern ones are a lot better performing. So one of them, or one general framework that can do this is graph neural networks. So for those not as familiar, in graph neural networks, you basically have your node state or the initial features basically of your nodes. Think of the nodes here as agents. And let's say we have 3 agents in this graph, and we assume a fully connected graph. You could also do k-nearest neighbor or any other graph in here. Then we consider some function at the edges. Let's say just a simple MLP that takes as input the receiver, the sender and the receiver features, basically the two ends of the edge, and compute some message. And then in this step 3, we basically aggregate all the incoming messages from your neighbors. You can use some permutation invariant function like max pooling, for example. And finally, you have your previous state and you have the aggregated message coming in, and you can do some node update, and for example, using a GRU. And so here is an example of an actual example. Internet is a work we showed earlier, which didn't model interactions. And then you can see how there's 2 vehicles that their future predictions at around 3 seconds, highlighted in red, are actually in collision. And you can see how for the vehicle on the right, the one that is left turning, you can see that our prediction is quite wrong with respect to the ground truth, which is plotted in gray. And when we add interaction, basically, essentially, we add what I presented in the previous slide with a graph neural network and keep the rest pretty much the same. Here we are changing the output parameterization, but don't worry about it. Just think of the ellipse, the center of the ellipse, as the equivalent of the left one. And what we are seeing here is that this mechanism now helps with understanding that, either the vehicle on the right will accelerate, right, and get through the turn quicker, or the other one will brake. And in this case, we predict that the vehicle coming into the intersection from the left is going to brake, and we predict more accurately the trajectory of the turning vehicle. Yeah, so here is just a quick demo of 2 vehicles turning, and you can see that they respect each other fairly well. The paths never really cross. And so, yeah, this is basically a success story for interactions. And I guess more recently, transformers have gained a lot of popularity, and you can view transformers as just a special case of graph neural networks, where you start with the same node features. We add what in transformer literature is called positional encodings, which are just some encodings, for example, encoding either the time step or like the position of those nodes, like the coordinates essentially. We replace the message passing as well as the message aggregation with just one operation, which is dot product attention. And then the update of the node state is just a very simple residual connection, summing the previous state and the offset of the state that we are predicting. And this is super lightweight. It's very heavily optimized these days in machine learning libraries, and scales. It's been shown to scale very well with data. So this is kind of the de facto architecture right now for interaction reason. And now that we've covered the 3, let's see actually how can we do this jointly, encoding the scene as a graph rather than each individual performing individual reasoning for these different subtasks. So basically, we can have this heterogeneous graph, like the one depicted in the figure. You can see in green the nodes for the lane graph. We have the agents. Actually, you can represent the agents as agents, or you can even represent their past waypoints, each of them as a node in the graph. And then we can have all sorts of connections, right? Like agent to agent, agent to map, map to agent, and map to map. And we can perform the same message passing that I just described in this heterogeneous graph. But one thing that I brushed over and haven't really talked about is that all these graphs are geometric graphs, geometric and topological graphs. They are not just like a social network where only the relationships matter. It also matters where the nodes are in space. And we haven't talked about in which coordinate frame we represent this. And so there have been basically two main methods up to very recently. So the first one is agent-centric, which means that for every agent, we process the scene from the perspective of that agent. And the advantage of this is that all the data now looks very similar because you are always looking from the same viewpoint, right? Like the viewpoint of the target agent you are predicting. And then because of that, for example, your predictions are easier because typically agents just move forward at the beginning and then maybe do something later, which we refer to here as viewpoint invariant. But the problem is this has low inference. We need to perform this encoding for every agent, right? And the alternative is scene-centric encoding, where you adopt some arbitrary reference frame. This reference frame can be the ego, for example, the position of the ego vehicle. This is typically what's used. And then you can do encoding just once, shared across all agents. So this is very fast, but it's viewpoint dependent. So essentially, if the ego, for whatever reason, is in a weird state, let's say a bit tilted with respect to the lane or performing a left turn that is not as common in the data set, your predictions are likely to be worse just because you haven't observed that many and it looks out of distribution to the model. And this also makes the training sample inefficient. You basically need a lot more data to train. And in the figure, when we basically change the coordinate frame, you can see that we are illustrating here that the predictions also change because your viewpoint is changing, the way you view the scene is changing. So you basically have different predictions depending on the viewpoint, even if the scene is literally the same. And very, very recently in the last year, there have been some methods that actually have achieved the best of both worlds by using these pairwise relative geometric encodings. The idea here is that instead of putting the geometric information in the nodes, you now move the geometric relationships into the edges. So the nodes only contain semantic information, but they don't contain coordinates. And then when you do the message passing and you are sending message from A to B, you can actually represent the coordinates of, let's say, A in the perspective, from the perspective of V, and the other way around. You don't need to basically consider any arbitrary coordinate frame where you perform this message passing. And this makes it fast. You only need to encode the scene once. It's viewpoint invariant and it's sample efficient for training. And what we are showing here is some results when you rotate the scene. So essentially we are modifying the ego or the arbitrary coordinate frame, right? If you perform scene-centric embedding, or here called global encoding, you can see how the predictions change and they are not robust, basically. And when we do what I just described, this pairwise relative geometric encoding on the right, the predictions just don't change over rotations because the scene is the same and the pairwise geometric relationships are the same. So viewpoint doesn't matter. And we get to the final part of the presentation. We are going to talk now about the output representations, the decoders that we can use to predict this, and some variations of the prediction task that have their own names because they are formulated slightly different. Essentially what we are after here is that we need to capture multiple futures. So for this object, in black, we've depicted different samples from the ground truth distribution, but that ground truth distribution, we don't have access to it. In the log, right, in driving logs, we can only observe one future, the one that actually happened, which is depicted in blue. And so this makes it challenging for training and also for evaluation. So for context, I won't get too much in detail about metrics, but what is done typically in prediction is that you predict multiple modes or samples, and then you evaluate actually the best one, the one that matches the closest to the ground truth. Because since we don't observe the ground truth distribution, you don't want to over penalize, let's say, predicting a left turn in this case, because a left turn here could have been perfectly fine, right? Like you just don't have enough information to tell whether it's going to go left or keep straight. So one option, a very simple one of the earliest works used, is to do autoregressive decoding. So this basically what this means is that we are modeling the one-step conditional distribution. We are predicting the distribution over the next waypoint, given our current state. And then once we predict the distribution, we can sample from it. And given the sample, we can predict the next waypoint, so on and so forth. The good part about this is that a very simple and parametric and unimodal distribution like a Gaussian can actually give you multimodal behaviors over time, because as you sample from it and condition on that sample, it will start diverging, right? And then if you get a sample on the other side of that Gaussian, it will start diverging the other side. So you can get multimodality with a very simple parametric distribution. But it's also it's slow, it's sequential over time. So if you have a long horizon and you need high resolution, this is going to be slow. And it also has compounding error. So basically, the same aspect that gives us the multimodality, it also makes it causes this distribution shift, because you get a sample and it's a bit unrealistic, let's say, for the behavior, and you condition on it, you get more unrealistic predictions, and this compounds over time. So the errors just get larger and larger. Actually, the most used representation right now in the leaderboards is this mixture of Gaussian trajectories. So this is a very simple representation. What we do is we have a categorical over k trajectories, and each trajectory is represented as a sequence of waypoints, and each waypoint is a bivariate Gaussian depicted with an ellipse in that drawing. So you can see, for example, a green trajectory with multiple ellipses and a blue one. Those are two different modes. And probabilistic training, if you train this with like negative log likelihood, you actually get a lot of mode collapse and instabilities because of the problem I mentioned that we only observe a single feature. And so to address this, typically a variety loss is used where only the closest mode is penalized and the score of the categorical, but not the waypoints of the other modes. Another option is trajectory sets. Here, basically, you have like a sampler based on your kinematic state, and you get a lot of candidate trajectories that an agent might execute. And the good part is that this is abstracting the regression problem. Now it's turned into a classification problem. You just need to predict which trajectory of the ones in the set is going to be the one that happens. So it's inherently multimodal because you now have, it's a categorical, right? And it's very easy to train with like just your standard cross entropy loss, for example. But it typically has limited coverage. So these samples for this to be efficient, the sampling process typically needs to happen offline, which means that typically you don't craft the samples to the map and the kinematic state of the vehicle, which means that you need a ton of samples to cover the possible behaviors that agent might take. More recently, actually, most of the best performant prediction models in the leaderboards, like Argoverse, use this goal-based paradigm where for each agent, we first predict the endpoint. Let's say we are trying to predict 6 seconds into the future. We predict the 6-second waypoint, and then from this waypoint, we also complete the trajectory. So given the initial state and the end state of the trajectory, now completing the trajectory is a very simple problem. And finally, we perform trajectory scoring to predict the probability of each of them. And the key here is that for the initial endpoint prediction, you can actually put a lot more expressive power and like basically a better network, larger network, or classification loss over, for example, lane graph nodes. And since that's the hard part, if you are able to solve that, the trajectory completion becomes easier. I think that's why these methods perform pretty well. And very, very recently, there's this, it seems like we are going towards this more refinement-based decoding where you start with some embeddings that at the beginning of training, they are just random mode embeddings, learnable. And we basically perform self-attention between the different mode embeddings as well as cross-attention to the scene, like let's say the lane graph and the past trajectories of the agents. That gives us some trajectory proposals. Then we can encode these proposals back into some embeddings, and we can essentially refine them. And the advantage of the refinement phase is that what's typically done is that you connect the agents or the past trajectories of the agent in that scene graph I was talking about to its local neighborhood, right? Like let's say the neighboring lane centerline nodes. But here, because now you're predicting these trajectory proposals, you can actually look forward where it's likely that the vehicle is going and also aggregate features from there. So it just has a better understanding of the scene that way. All right, so far we've talked about prediction as if the ego vehicle almost wasn't there, right? But actually the ego vehicle is part of the scene and it has a lot of influence on the other agents too. So what we are showing here are what we call marginal predictions. This is just prediction, what we were talking about earlier. And so the self-driving vehicle is at the top, and then there's a vehicle coming through the on-ramp, and it's supposed to yield. But our predictions say that, I mean, it might slow down a little bit, or it might be a bit faster. And then what the planner can do here really is just plan a trajectory that is safe, right? So it needs to brake because it looks like everything is occupied. But in practice, actually, that's not the best solution, because these two predictions that we had for the other agents come from two completely separate modes of how the scene might unroll in practice, or the data generation process, right? On the top, you can see that we actually went and accelerated, and therefore the other vehicle yielded to us. And on the bottom, you can see the case where maybe we actually were cautious and broke a little bit, and then the other agent decided to go. And as you can see, neither of the two futures, the true possible futures, in neither of them, the vehicle had to brake as hard as in the marginal prediction case, where we consider everything to be kind of possible, and then everything looks occupied, and so there's no better solution. So formalizing this task a bit more, the ego here will be the blue actor, and we are considering different query agent futures. So because we have some control over our future actions, right? We can essentially query what would happen if I did this, what would happen if I did that instead. And what you're seeing on the red car is the marginal predictions, the ones without considering this interaction with the ego, say that this vehicle is likely to just keep straight and going fast, right? But once we condition, we get these conditional predictions in red, which actually capture the actual ground truth, which is that the vehicle nudged to avoid being on our path. And I think the first work that proposed this, or at least an early one, is this planning for trajectory prediction. And so in the traditional pipeline, you have the planner in red, which has some trajectory generation typically, and it considers a set of trajectories. And then we have prediction being completely agnostic to that. And then there's a cost function that takes our candidate trajectories and the predictions and evaluates them. In this new paradigm they propose, basically now the trajectory generator output also gets into prediction. So essentially we are predicting what might happen for the different potential plans. And then the cost function can take these conditional predictions instead of the marginal ones, which should be beneficial for more effective and efficient driving. However, this in practice is not as easy as it sounds. You would hope that you just put the features together of the ego somehow, and this works great. But in practice, let's say you get these marginal predictions, just doing regular prediction, not conditional, which makes sense, totally makes sense. And then let's say you condition on the ego. Let's say the ego vehicle is the one with the blue trajectory. You condition on this potential plan that you have that you're going to break. And what many papers found that you see in the predictions is that then you predict that the vehicle on the left will also break, even though the traffic light is green. And this is basically a causal confusion problem. There's a correlation versus causation. So essentially in the data, every time the ego breaks, it didn't break for no reason. It broke, let's say, to stop for a traffic light, right? So it learns that if the vehicle on the right brakes, the vehicle on the left, it's also likely to brake, even if there's nothing ahead. And actually getting rid of this is very hard. I don't think I've seen any paper that really solves this. There's some progress with respect to what I just presented, but won't be covering that. But it's still very much an open problem today. And also some consideration is that this is very demanding computationally. You need to run prediction for every conditional, or for some conditionals you can summarize perhaps the actions of the ego, but it's not trivial. We end up also with many predictions which also need to be considered by planning, making overall the pipeline very expensive. And so another potential form of prediction is joint prediction, where let's say we have these two vehicles A and B. And now instead of predicting multiple futures for each vehicle separately or conditioning on the ego, we are just predicting these joint futures of the scene. So here we are showing three potential unrolls of the scene in orange, purple, and green or blue. And essentially, each of these futures is a joint future. It's a sample of what all the agents in the scene could do. And now, instead of evaluating this by agent by agent, and considering the mode from the agent that is closest to the ground truth, now the task is a lot harder, and we are actually trying to predict a joint mode, a joint sample that matches very well the ground truth. So in this case, for example, for vehicle A, the orange prediction is the best. And for vehicle B, the purple prediction is the best. But jointly, the blue predictions are the best ones. So one approach to model this in a generative way is that we have the agent features. Before we were representing them with those like little feature vectors. Now we call them x1, x2, x3 for 3 agents. We have a graph neural network or transformer acting as the latent prior, which predicts this distribution over latent codes. From this distribution, we can sample different futures and basically, or different latent codes. And each of these latent code, we can map it into a future trajectory for each actor based on this another graph neural network decoder. And if we keep sampling, which we can do infinitely from this continuous random variable, we get different futures. And here, for example, you are seeing in red, it's a future where the vehicle supposed to yield actually yields, and in blue, a future where this doesn't happen. And these are actual outputs from this model. We were very impressed that it was able to pick up on the fact that depending on the future traffic light states, which we don't know about, the scene might unroll very different jointly. So on the left, you have the case where the traffic light turned green for the vertical traffic, the ones doing the left turn. And on the right, you have the case where actually that traffic light turned red, and now the horizontal traffic can proceed. And again, like the model here doesn't know anything about traffic lights actually. Not even the past one, like the history of the traffic light, but definitely not the future one. And because we have this continuous random variable, you can also interpolate in between 2 samples. So you interpolate in latent space, you consider multiple latent samples in between the 2 you are considering, and then you can decode each of them. And that's what we are plotting here. And you can see that, for example, on the top left, even though the latent is continuous and it's supposed to be like, the interpolation is smooth, right? We are just doing linear interpolation here. The output space snaps very well to different behaviors. So for the vehicle going north, we are basically predicting it can go faster or slower, but it's actually very correlated that if it goes slower, we predict a right turn. And then suddenly if we go faster, it snaps to continue straight. So it has a very good understanding of the overall relationship with the map. The other agents do in the other example in the top right, for example. And here what you are seeing is these predictions, this genetic model, I believe 50 samples just squashed like basically one on top of each other. And yeah, again, like this would be the equivalent of predicting marginals instead of joint, right? We are just essentially putting everything together for every agent. And it qualitatively, these results were a lot better than the state of the art back at the time. And however, like these generative models, they can be really good at modeling the data distribution, but it can be a bit hard to deploy to an onboard system, namely because in an onboard system, you want everything to be deterministic for safety. And you also don't really care that much about the most likely outcome. You care about a range of diverse outcomes. And in particular, you want to analyze the risk level of your plan. And so sometimes you want to predict more diverse outcomes rather than the most likely ones all the time, which is what you would typically get from a generative model unless you sample a lot. And so I won't go into too much detail, but feel free to check these out. We basically can learn a diverse sampler that is deterministic to propose different latent sample instead of randomly sample from the distribution. We can also do mass sequence modeling style processing to model this joint and have a fixed number of modes that we're predicting. And finally, we can also recombine the marginal endpoints. So if we have marginal prediction models and we have the endpoints of it, we can just recombine them into joint modes. The idea here is that the marginals already capture all the uncertainty and you only need to combine them into joint futures. And this is the final part. We are here considering a completely different representation. So we are moving away from trajectories into occupancy. So you can think of semantic segmentation in bird's eye view over time. And the architecture on the left part pretty much is unchanged. We extract LiDAR features, map features, we fuse it. And then we just have some simple network. In this case, it's recurrent, but it could be just a convolutional neural network that outputs these semantic maps. And so in these semantic maps, each pixel in bird's eye view basically tells you the probability of that pixel being occupied by some particular class, like let's say vehicle or pedestrian. And we can train like multiple of these semantic segmentation maps, one for each time step into the future. And the good part is that it's super close to the planning, what planning cares about. Like, let's say if you want to cause the collision of a planned trajectory, you can just take the dot product between the ego position and that probabilistic map, and that will give you basically the probability of collision. We can improve a bit on this. Instead of predicting occupancy directly for all the future, we can predict occupancy for the current time step, just perception of the occupancy without forecasting. And we can predict the motion over time. And then we can use the motion to flow, basically to warp the occupancy into the future. And we can do this basically autoregressively. And that will give us the future occupancy too, and consistency between motion and occupancy. And the reason why motion is interesting is that planning doesn't care only about collision. You also need to keep, let's say, a safe headway with the vehicle in front. So this motion actually can be used to make sure that your velocity makes sense with the actor in front of you. This very naturally, with a very simple training based on like cross-entropy laws, just the classification laws, gives very multimodal future. So for this agent, we are predicting it can right turn, left turn, or go straight. We are not really predicting for this agent on itself. We are just predicting occupancy at the scene level, but the network is able to infer like basically the agents. The agents plot in gray are just the ground truth instances for reference, but all we are predicting is that heat map shown over time. And the same for this pedestrian, we can predict it might go into the crosswalk or it might turn right. And this is actually one of my favorite. It can learn about occlusion automatically. Basically, we don't get any LiDAR point there because of the vehicles that are occluding it. And we are predicting some residual probability because we think there could be someone there. We've learned basically that parked cars are on the side of the street. And because we don't have information, we still predict some occupancy. And finally, so that was all supervised. But actually, this paper does a very smart self-supervision. So from LiDAR points, you don't get the occupancy directly, but you do get this egocentric free space on the right. Basically, you get a visibility map of the scene. And then by doing differentiable ray casting, you can actually obtain what they call an emergent occupancy by training on the egocentric free space without any labels. And of course, this is good because this is great because you can scale the training up. You don't need annotations. The downside here is that all your occupancy lacks semantics. You only have like geometric occupancy, right? But you don't know if it's a vehicle or if it's a pedestrian. But you could potentially do that as a fine-tuning stage. And finally, this is a work that we are presenting at this CVPR tomorrow, Tuesday. And the main motivation is that although very expressive, these occupancy models I was presenting are very memory hungry. You need these very dense tensors over time, and you need very fine resolution as well, because these are going to be used by the planner to plan like narrow maneuvers, right? So you can have a pixel size of like a meter, for example. So to tackle this, we instead represent occupancy as a continuous 3D function. X, Y are positions in bird's eye view here, and time, T, is the time over the future horizon. And we can predict, basically our model predicts a scale for this query point. It predicts a scalar occupancy and a two-dimensional flow vector. And the way this is intended to be used is that the planners actually don't care about the occupancy in the whole scene. They just care about what happens around the trajectories they are planning, right? So if we have these candidate trajectories in black, we can define these query points, and then we can query our model in parallel for all these query points to get the occupancy and flow at those positions instead of querying essentially everywhere in the scene. And one challenge to do this is that for the future query point, let's say here, we are querying this for occupancy at 5 seconds into the future. Of course, there's no LiDAR evidence at that region, right? Because the LiDAR evidence is at the current time, not the future time. And so what we proposed is a global attention mechanism using basically the formable attention so that it can attend to back where the LiDAR evidence is to predict the occupancy of this point in a very efficient way. And I won't go into the details of the whole architecture because it could be a lot, but feel free to drop by our poster tomorrow. And here are some results. This is the equivalent of, if you're familiar with segment anything model from Meta, for example, this is the segment everything mode, where basically we are querying for every position in space our model just for interpretability and to display it on a screen, but the planner could just query whatever he wants. And you're seeing the occupancies over time, the predicted occupancies over time. So yeah, in conclusion, the foundation is to learn a very rich representation of the scene. We can do this from past context and from the map, as well as reasoning about interactions between agents. And finally, joint perception and prediction is better than the traditional pipeline in that it can both use the tracks, but also the sensor data directly. To capture uncertainty and multimodality, we need to do it for safety because these are all the options that might happen, so the planner needs to be informed about them. And so it allows us to measure the risk, basically, of a candidate maneuver. And we saw that conditional prediction is a promising avenue to be able to plan more efficient maneuvers that are not overly conservative, but still safe. We talked about seeing consistent predictions and how this can basically capture the multiple futures separately, not just at an agent level, but at a scene level. And we will see in the planning session later, presented by my colleagues, that this enables non-conservative planning with contingencies, which basically means that instead of planning a single trajectory, you can plan a set of branching trajectories from it that consider the worst case, but also the expected case. And finally, we talked about occupancy as an alternative that moves away from the traditional representation of objects and trajectories and can capture uncertainty potentially better. Thank you so much for your attention. I know it was a long presentation, but thanks for all that. That's it.
We have time for one question, and then we can switch over to motion planning and controls.
So thank you so much for your presentation. There to the conditional here prediction, doing prediction for the scene, but you're only considering the influence of the ego vehicles, separating vehicles to the other agents. But it is possible to consider the future of each agent that influences on the future of all agents, not only the ego vehicle.
Yeah.
Because at this moment it's passive motion prediction around the world. Then we are studying now conditional behavior prediction of only the ego vehicle. But what's going to happen when there are more self-driving vehicles on the road?
Yeah, that's a great question. Actually, in conditional behavior prediction, as you mentioned, we only condition on the ego behavior. But on joint prediction, we are attempting to describe this scene as a whole. So joint prediction is a very important or promising avenue for this problem that you ask. The challenge here is that in joint prediction, a generative model like the one I presented, for example, you can only sample from it and get like candidate futures at the scene level, where everything is like joint conditional on each other. But it's hard to then condition on some predefined, let's say if you already know the behavior of some of the agents, because let's say they are robots and they can communicate between themselves, so you actually know what they plan together. I think that I haven't seen a paper that studies that, but that would be interesting. Yeah.
Thank you so much.
Thank you.